What's up, guys, and welcome to this video on the 2019 supplementary exam. We're going to cover question 8, a nice and short question, 16 marks, and the question is on photons and electrons. Okay, and I've copied the part of the formula sheet that we get. Okay, so let's get into reading the question. Okay, so physics student measures the maximum kinetic energy of photons emitted from the surface of material X using different frequencies of the incident radiation. The student uses his data to plot the graph shown below. Okay, so cool stuff. We've got a nice graph. Yeah, we've got a nice graph, we've got a table of metals, and we've got the work functions. Okay, and the first question is a freebie. It's asking for the definition of the work function. Okay, so the question is, do I give you the definition? Okay, fine, I'll write it out. 8.1. Okay, so the work function is the minimum amount of energy needed to emit an electron from the surface of a metal. Okay, so if the energy is less than the energy of the work function, then no energy or no electron will be emitted. Okay, so this is pretty much that point, or relates to that point rather. Okay, so 8.2, state the independent variable. Okay, so the independent variable, what is the independent variable? Easy way to remember it, it is the variable we change. Okay, and in this case it would be, let's see, using different frequencies of incident radiation. So the answer is in the question, it is the frequency of incident radiation. Okay, so that is our independent variable, and another 2 free marks. Okay, question 8.3. Okay, show that the gradient of the graph has units of Newton meters seconds. Okay, so first of all, our gradient is equal to our change in y over our change in x. Okay, so we're worried about the units. Okay, so the units of, so our change in y is here, change in x is here. Okay, so the units are going to be joules over hertz. Okay, but we also know that frequency is equal to 1, or is the inverse of time. So 1 over, so 1, okay, knowing this relationship, we can say the hertz is equal to 1 over seconds. So 1 over hertz is equal to a second. So this is equal to joules seconds. Okay, so joules times seconds. Okay, that's not erasing for some reason. Joules times seconds. Okay, we also know that a joule is equal to a Newton times a meter times a second. Okay, if we didn't know this, or an easy way to remember this, joules are units of energy. Okay, what's an easy form of energy? Let's take EP. Potential energy is mgh. Okay, m and g is a Newton, and h is a meter. So the units of joules is equal to Newton meter. So we have Newton meter seconds as our answer, and we've proven that. Cool stuff. Okay, then it says use information from the graph and the table above to determine the identity of metal X. Okay, so usually when they introduce a definition beforehand, we will most likely be using that somewhere in this question, and this is where that comes out. So let's do question 8.4 right here. Okay, so we know that the work function W naught is equal to a formula H, Planck's constant, times F of naught. And this point here is F of naught. Okay, so now we just need to substitute values in, and we get Planck's constant equaling 6,6 times 10 to the minus 34 times our F value, or F naught value, which is 1,05, don't forget, times 10 to the minus, or times 10 to the 15 hertz. And plugging that into a calculator, we get a value of 6,93 times 10 to the minus 19 joules. Okay, and if we look in the work function, it's pretty much equal to that one right there. Okay, or the closest one is that. So we can say, therefore, metal X is zinc. Cool stuff. And we've got 4 marks right there. Okay, and now we move on to question 8.5. The wavelength of blue light is given as that. Okay, so lambda is equal to 475 nanometers is times 10 to the minus 9 meters. Okay, when the blue light is shone onto a certain metal surface, the maximum velocity, EK max, is given as 2,77 times 10 to the 5 meters per second. Determine which metal from the table above is being used. Okay, so for this 8.5, let us go and find a formula that works. Okay, so we have EK max and we have lambda. Okay, or yeah, we have the wavelength, and from the wavelength, obviously, we can get E, or we can use that form as well. Okay, so what we're going to do is we have EK max. I'm going to use that formula right there, but I'm going to manipulate it to get EK max as our subject. So EK max is equal to, okay, that's E minus the work function, W naught. Okay, but I'm going to say that E is equal to HF minus the work function. Okay, and obviously EK max is half mass times velocity squared. Okay, we know the mass of an electron, we know the velocity, we know the value of H, and okay, so F we're gonna substitute this essentially, HC over lambda. So let's write that out as well. So let's just say half mass of electron velocity of electron squared equals H C over lambda minus the work function. Okay, then what we have is a half. The mass of electron is 9.1 times 10 to the minus 31 times 2.77 times 10 to the 5 was our velocity, is equal to H, we know is Planck's constant, it's 6,6 times 10 to the minus 34. C is the speed of light, which is 3 times 10 to the 8 over our lambda was 475 times 10 to the minus 9 minus the work function. Okay, now we just solve for the work function, and we get that the work function is equal to the work function is equal to 3,82 times 10 to the minus 19 joules. Okay, so now we go to our table. Let's see, 3,9, it's pretty much sodium, so we can say, therefore, the metal is sodium. Okay, and that is our answer. Actually, I'm going to box this because that's our full answer. Okay, and there we go. And just like that, we get our 16 marks. Okay, so yet again, photons and electrons, not too difficult of a section. It's quite nice and straightforward. And yeah, so I hope this was useful, guys. Thanks for watching.